In the early 1970s, the population of the Taipei area was approximately 2.5 million. Each year, as the early summer drought season arrived, the city frequently experienced shortages in tap water supply, often necessitating zoned water rationing. This situation caused significant inconvenience for urban residents. With the rapid growth of industry and commerce in Taipei and the accompanying population surge, the demand for tap water increased dramatically. To resolve the shortage problem, the Taipei city government began construction of the翡翠Reservoir in 1979 on the Beisha River, located approximately 30 kilometers from downtown Taipei. Because the reservoir's dam was a high dam, its construction quality and project management were of critical importance to the safety of the Taipei area. As such, then Premier Sun Yun-swan instructed that the project be entrusted to Taiwan Power Company for execution, with Sinotech engineering consultants responsible for design and supervision, and construction carried out by the Retired Servicemen Engineering Agency. Upstream of the翡翠Reservoir's Arch Dam, the catchment area covers approximately 303 square kilometers, with a storage capacity of around 406 million cubic meters. The reservoir was primarily built to supply tap water for the Taipei area. The project layout included a main dam, auxiliary dam, energy dissipation basin, power plant, diversion tunnel, and a temporary dam. The main structure includes an arch dam, standing 122.5 meters high with a crest length of 510 meters, a base width of 25 meters, and a crest width of 7 meters. It is a thin double curvature variable thickness arch dam, constructed with a total of 706,000 cubic meters of concrete. A power plant was also built, equipped with a 70,000 kilowatt hydroelectric generator utilizing the reservoir's water pressure, providing additional benefits from the reservoir's construction. In addition, the reservoir is equipped with 8 spillway gates, installed at the center of the arch dam crest, each fitted with a steel radial gate. A secondary dam is located approximately 200 meters downstream of the main dam. It is also an arch dam, standing 28 meters high with a crest length of 237 meters. Together with the main dam and the flanks of the riverbanks, it forms an energy dissipation basin. During flood discharge from the spillway, the water in the basin helps absorb the impact of the released flow. The entire basin floor is covered with a 2-meter-thick concrete lining for protection. The翡翠Reservoir's auxiliary works included a diversion tunnel, measuring 386 meters in length and 10 meters in diameter. During the construction of the main structure, this tunnel was used to divert the river flow around the construction area, allowing the site to remain dry and facilitating construction. An upstream temporary dam was also built, standing 29 meters high with a crest length of 202 meters. It too was an arch dam, constructed during the initial phase to block the stream and direct water into the diversion tunnel. It served as a supporting structure for the diversion tunnel. In mid-1981, the main project was entrusted to the Reservoir Engineering Agency for management and construction. Initial efforts were focused on the rapid completion of the diversion tunnel and upstream temporary dam. The diversion tunnel was completed and began conveying water in March 1982, while the upstream temporary dam was completed in October 1982, thereby fulfilling its role of water interception. Both the diversion tunnel and the upstream temporary dam were indispensable auxiliary facilities for the reservoir project. After the reservoir began impounding water, both structures were submerged beneath the surface. The first stage involved the foundation excavation for the dam abutments on both riverbanks. On the valley walls flanking the riverbed, along the designated foundation lines of the dam, 2 keyways were excavated vertically from top to bottom. All weathered surface rock was completely removed to expose sound and intact bedrock within the keyways. This ensured that the dam concrete could bond directly with unweathered rock, allowing the foundation to fully withstand the stress transmitted from the dam structure. The keyways had a vertical depth of 122.5 meters and were excavated using the step method, with each step measuring 6 meters in height. Using the latest crawler-mounted drill rigs, holes were drilled along the perimeter of each excavation step on the keyway surface, and pre-splitting blasting was employed to carry out the excavation. Along the excavation edge, at 50 to 60 centimeters intervals, angled pre-split holes about 7 to 8 meters deep were drilled. In each pair of adjacent holes, one was loaded with pre-split explosives, while the other was left empty. Within the keyway area, on the surface, blast holes of equal depth were drilled at intervals of approximately 1.5 to 2 meters in all directions, front, back, left, and right, and blasting was carried out step by step from top to bottom. After the rock was fractured by blasting, heavy bulldozers pushed the loosened material layer by layer from the inside outward toward the slopes. Then the next step of drilling for pre-splitting and blasting began. This sequence continued downward, step by step, until the lowest excavation level at the riverbed was reached. The surfaces resulting from pre-splitting blasting were smooth and precise, like cut by a knife, with no damage to the integrity of the surrounding rock. Because the side slopes of the keyways were exposed to air for extended periods, to prevent the rock surface from weathering due to prolonged exposure, shotcrete protection was applied extensively to the cliff face. Workers were suspended by ropes from the top of the slope to carry out the spraying operation across the entire surface. The process was truly breathtaking, revealing the courageous and daring spirit of the civil engineering personnel. The bedrock in contact with the翡翠Reservoir Dam is composed of fine-grained sandstone, which possesses excellent engineering properties. It is considered the most suitable dam foundation for arch dam construction in the Taipei area. However, its only flaw is the layered structure of the rock. Between these layers are joints filled with softer materials, such as silt or gravel, with thicknesses ranging from less than 1 centimeter to as much as 50 centimeters. These joints, located within the stress-bearing zone of the dam foundation, represent the weakest link for stress transmission and therefore must be removed. To accommodate various cleaning and backfill grouting operations, horizontal access tunnels were excavated into the slopes driven laterally into the strata from the slope surface. Tunnels were spaced at approximately 8-meter intervals, with a total of 18 tunnels excavated. These access tunnels intersected with multiple vertical working tunnels, forming a crisscross network totaling nearly 6,000 meters in length, distributed throughout the rock layers on both banks. Depending on the thickness of the joints, 3 different cleaning methods were adopted for this project: Method A, Method B, and Method C. After the joint treatment in the working tunnels was completed, the working tunnels, along with the access tunnels, were sealed with concrete to ensure no voids remained within the foundation. The tunnels were filled section by section, proceeding from the innermost point outward. To prevent loose contact between the tunnel crown and surrounding rock, contact grouting was also carried out. Although the foundation rock had been treated within the strata, the natural rock structure inevitably contained some undetectable microcracks. Therefore, drill rigs were installed on the foundation rock surface, and blanket grouting was conducted, drilling into the rock layers and injecting cement grout to completely fill all the gaps within the load-bearing zone of the foundation. To ensure a tight bond between concrete and rock, the rock surface had to be thoroughly clean and dust-free. For this, the project employed water jets at 7 kilograms per square centimeter of pressure to wash the surface. In areas where rock scale adhered too firmly to be removed by water, steel brushes were used to scrub the surface, ensuring the required level of cleanliness was achieved. When pouring the first layer of concrete onto the rock surface, wooden formwork was used to accommodate the uneven contours of the rock. Above the foundation layer, custom-designed cantilevered steel formwork was used. As concrete was continuously poured, the dam gradually rose in height. The total volume of concrete used in the翡翠Reservoir project amounted to over 1 million cubic meters, requiring an immense supply of gravel and sand. To meet this demand, a quartzite quarry located about 10 kilometers upstream of the dam site was designated as the source of stone. Using controlled blasting, the quartzite was broken down into blocks smaller than 90 centimeters, which were then transported to the primary crusher and crushed into smaller pieces under 20 centimeters for storage. Depending on the required particle size, the material then underwent further crushing, washing, screening, and spraying to ensure the quality of the aggregate. As the source of construction materials, the production of these aggregates was carried out by a modern, fully automated crushing plant, capable of producing approximately 320 tons of various grade aggregate per hour, the largest and most advanced crushing plant in Taiwan at the time. A storage facility was built within a narrow valley with the capacity to hold 5,000 cubic meters of aggregate in various grades. Dump trucks transported the qualified aggregate to the lower side of the storage facility. Once dumped into the feed hopper, the material was entirely conveyed by automated belt systems into the storage bays and then transferred to the batching tower on the dam's right bank. Beside the batching tower, an ice-making plant was established to regulate the temperature of the concrete used in dam construction. According to the regulations, the temperature of the concrete during pouring had to be maintained below 19 degrees Celsius. To achieve this, crushed ice was produced and used as a substitute for mixing water, ensuring effective temperature control. The batching plant operated on a fully automated computerized system. By simply pressing a button on the control panel, concrete of various specified strengths could be produced. Aggregates of different grades were automatically measured, mixed, and batched according to the prescribed ratios. The maximum concrete output reached 120 cubic meters per hour. Due to the massive volume of the dam structure and the high-speed placement required for the concrete, cableway cranes were used for transport and placement. After mixing, the concrete was loaded into specially designed railcar buckets, which were transported along a dedicated platform to the cableway crane station. There, the concrete was automatically discharged into suspended buckets. Each bucket could carry 4.5 cubic meters of concrete. Once lifted, the bucket would traverse along the cableway to the designated concrete placement point on the dam. The bucket was then lowered, and the bottom gate released to pour the concrete into place. The bucket would return immediately to the platform to reload the next batch. Each cycle took only 6 minutes on average. The dam was a double curvature arch dam, with curves in both plan view and vertical profile. To precisely control the shape of the concrete dam, the structure was divided into 29 blocks for ease of placement. In the vertical direction, the dam was segmented into lifts of 2.5 meters, with a total of 961 lifts. During formwork installation, layout points were set every 1.5 meters along both upstream and downstream edges. Across the 961 lifts, there were a total of 22,488 layout points. This meticulous design and execution ensured that the dimensional deviation of the dam body remained within 1 centimeter, resulting in perfectly smooth, curved surfaces on both sides of the dam. In the lower section of the dam, each lift of concrete often exceeded 1,000 cubic meters in volume. However, each concrete bucket used for placement could only hold 4.5 cubic meters, and the time interval between each bucket was typically more than 6 minutes. According to construction specifications, the time gap between successive layers of concrete must not exceed 90 minutes. To address this constraint, a more complex stepped placement method was adopted. The placement location for each bucket of concrete had to be prearranged, and concrete was poured strictly in sequence without deviation. Once a bucket of concrete was placed at its designated location, a vibrating rod was immediately inserted vertically into the fresh concrete. This served two purposes: first, to spread the concrete evenly through the motion generated by vibration, and second, to densify the mix by removing trapped air. Care had to be taken to ensure the vibrator did not contact any embedded components. Each lift of concrete was to be completed in one continuous operation, to avoid cold joints caused by placement interruptions. After completing a lift, the next lift could not be poured immediately. Sufficient time had to be allowed for the concrete to set. Typically, the next lift was not poured until 72 hours later. During the first day of curing, concrete often exhibited a phenomenon called bleeding, where water molecules rose to the surface, forming a slurry-like film that severely affected bonding with the next lift. In earlier dam projects, this film was typically washed off about 6 hours after pouring, using water jets at a pressure of 7 kilograms per square centimeter. However, further research showed that new bleeding continued to occur beyond 6 hours. Thus, in this project, high-pressure water cleaning was carried out 24 hours after pouring, using water jets at 420 kilograms per square centimeter. The cleaned surface became as clean as new, and no further slurry formed after that point. This high-pressure cleaning machine was a specialized piece of equipment not available on the general market. After the completion of each concrete lift, shower-type water spraying was immediately applied for curing, and the curing period lasted more than 3 weeks to prevent moisture in the concrete from evaporating. As concrete sets, it generates a significant amount of heat, commonly known as heat of hydration, which causes a substantial increase in the dam's internal temperature. To prevent cracking of the dam body due to a gradual temperature drop after completion, which could compromise structural safety, several thermal control measures were adopted. These included the use of Type II low-heat cement, a pre-cooling method in which crushed ice was substituted for mixing water, and a conduit cooling method where cold water was circulated through the dam body. In the conduit cooling system, thin-walled steel pipes, known as cooling pipes, were laid across the surface of each concrete lift with an average spacing of 1.5 meters. Each pipe had a diameter of 25 millimeters and a maximum length of 300 meters. During installation, it was essential to ensure that the cooling pipes uniformly covered the entire surface area of the concrete lift. For large area lifts, 2 cooling pipes could be installed side by side. Only after the cooling pipes were in place could the next lift of concrete be poured. As soon as pouring began, cold water was introduced into the pipes via the exposed pipe outlets on the downstream face of the dam. A dedicated cooling water facility was built on the right bank of the dam to cool clean water before circulating it through the system. Through insulated steel pipes, cold water was continuously introduced into branch pipes on the downstream side of the dam, which were then connected to the internal cooling pipes. As the concrete cured, it continuously generated heat of hydration, resembling a mist rising from within. This heat was absorbed by the cooling water. Along its path, the water absorbed the heat radiating from the concrete surrounding the pipes and was then discharged through the pipe outlets on the downstream face of the dam. This water cooling process had to be continuous and uninterrupted. The concrete's internal heat was steadily absorbed by the circulating water, thus achieving the intended cooling effect. To prevent uneven cooling, the inlet and outlet of the cooling water were reversed every 12 hours. The temperature of the cooling water had to be at least 10 degrees Celsius lower than the concrete temperature. At any given time, approximately 20 cooling pipes were active in circulating water. The conduit cooling process was carried out in 3 phases. The first phase, or initial cooling, began immediately after concrete placement and lasted for 2 weeks. The second phase, or intermediate cooling, was carried out sometime after the second week, and lasted for approximately 30 to 50 days. The third phase, or final cooling, lasted for around 50 days. After the final cooling phase, the temperature of the dam body was brought down to 14 degrees Celsius, the required temperature for grouting the vertical contraction joints. The vertical contraction joints on the dam body, at 14 degrees Celsius, would open to a width of approximately 5 millimeters, as calculated based on the concrete shrinkage coefficient. If these joints were not filled with grout, the dam blocks would remain independent of each other, and when the reservoir began impounding water and applying pressure, the dam would be unable to function as an arch. Therefore, once the dam body cooled to 14 degrees Celsius, grouting had to be performed immediately to unite the blocks into a single monolithic structure. Thanks to the joint efforts of the Reservoir Engineering Agency personnel, the翡翠Reservoir achieved its initial water impoundment target in February 1985, and began supplying tap water to the greater Taipei area, resolving the region's chronic summer water shortages. By the end of March 1986, the diversion tunnel was sealed, and full-scale water storage began. The翡翠Reservoir has a total storage capacity of 406 million cubic meters, and is projected to meet Taipei's tap water needs through the year 2030. From planning to design and construction, the翡翠Reservoir was entirely completed by Taiwanese professionals using local expertise, making it the first large-scale arch dam in Taiwan to be built solely through domestic effort. To construct this dam, the Reservoir Engineering Agency worked arduously day and night, and ultimately completed the reservoir in 1986. From that point on, residents of the Taipei area were freed from the hardship of water shortages. As we enjoy the precious and abundant water supply today, we should feel immense pride in this monumental achievement in the history of Taiwan's civil engineering. We should also hold deep gratitude for everyone who contributed to this remarkable project, and above all, we must thank the Reservoir Engineering Agency personnel, who braved all hardships and overcame every obstacle to build this perfect reservoir for the nation.